My name is Sogol Haghighat. I am a research scientist at Fraunhofer IAIS, which stands for Intelligent Analysis and Information Systems. And this was a collaboration between our institute and CERT. And as part of this project, we basically try to look into a kind of a more specific form of transfer learning, which is from image domain to a video domain. For that, we built a transformer-based video classification, which has a self-supervised feature extractor. Just a very quick overview on the different topics that are involved in this project. First of all, the knowledge transfer or transfer learning, basically. It is not a new thing, but every day there has been more focus also on transfer learning using unsupervised models and self-supervised models, which are trained on large amount of data sets using some predefined pretext task or a way to basically avoid having a lot of labeled data and just rely on unlabeled data and create more generalized pre-trained models. And more of the experimental studies that have been done to see how well these models now can transfer knowledge to other tasks have been focused on image-related tasks. For example, if the model was trained on image classification data sets, they have done a lot of research on now checking if it works for object detection as well, or other like segmentation, etc., all more or less image-related topics and tasks, downstream tasks. That's why extending the idea of using these self-supervised models, which are based on contrastive representation learning from image tasks to video tasks, is something that is kind of recently been gaining more attention. On the topic of video classification, for dealing with video per se, because video has basically multiple frames coming one after the other, then that is what forms a video. There are many ways to kind of embed or represent a video. There are ways to use 3D convolutional neural networks to basically represent the video. An example would be this framework CVRL, which is actually a contrastive video representation learning framework, which was trained on kinetics dataset. VideoMoko, another framework, which is again also based on the idea of using contrastive loss or contrastive representation learning, but combining it with LSTM to be able to apply it to the video or the other dimensionality, which is time. As well as that, researchers have also looked into using transformers as a way of encoding multiple frames in a video into like one single representation per video to use it for example, action recognition, video classification, etc. Other approaches such as this framework or this network will use FrameExit will use some strategy to sample deterministically from the video so that there are only, for example, 10 or only a few frames sampled, and then some feature pooling is applied to combine them together and make one representation. So there are a variety of methods used in the literature to actually create one single embedding from the from videos. But what was the motivation of this task? So even though knowledge transfer has or transfer learning has been studied within the image related task quite a lot, considering when these models are trained on such large data sets, we wanted to know if they are capable of generalizing to other domains, such as video-related tasks, if they can be reused as they are without having to fine-tune them or adapt them in any way, as they are trained on image data sets, directly use them for video-related tasks, such as video classification. And if that will lead to having then more lightweight, affordable training pipelines, which then can be repeated with other data sets, which are again relevant for that video, or other downstream tasks, which then will need a slightly different detection head, for example. So as part of the contribution, we actually looked into this family of self-supervised pre-trained models on ImageNet datasets, CMCLR version 2. They actually offer like adaptable kind of wider or narrower, deeper or shallower networks, as well as a mechanism called selective kernels. Basically, they have quite a few pre-trained options available already with the ResNet backbone, ResNet 50, 101, and 152. As well as that, a transformer-based architecture, a lightweight architecture was designed for this task, which basically takes frame level features and generate a will give a prediction at the video level. This transformer-based network was also, because in variety of video-related transformers, a same number of frames are sampled from every video, and that would be problematic when videos in the dataset have different lengths, and some videos will have more samples even though they're shorter in contrast to the other ones. So it is also possible to sample varying number of frames from each video, and the padding would be activated later on to make it work for the transformer network or the transformer encoder, basically. This is the overall look of the proposed framework. It has two main stages. The first stage is the feature extraction, which is not a trainable stage. Well, it does not need training, basically. A number of frames from video are sampled, and this number actually we did as part of the ablation study. We did some experiments to find out the efficient or the relevant number of frames that are required to sample for a particular data set. But for now, if n frames are sampled from each video, they just go through this pre-trained model, this encoder, and frame level representations will be produced. And that is just an inference run. And the second stage is a classification stage, which allows encoding all of these frames into one single representation, which then represents the video. And for that, a dimensionality reduction as well as a video transformer encoder is applied to them, to these to the sequence of embeddings. And this dimensionality reduction is mainly because what comes out of these models are relatively large embeddings, 4096 in size, and to make them actually more suitable for the transformer encoder, as well as slightly adjust them because this dimensionality reduction layer is actually trained with this classification head, and it offers a slight adjustment to the target data set. It works as a slight form of fine tuning, and we actually also have proved it to work better if we have this layer of dimensionality reduction by doing some more ablation study without any dimensionality reduction, and etc. And as it was also explained in the first talk, the CLS token is basically the token that represents basically this is the embedding of the video. It has the context of all the tokens, and that is used to make a prediction on the video, what action it was detected in this video. Here in this image is the details of the transformer encoder. As mentioned, when the input embedding matrix will go through the dimensionality reduction, these reduced embeddings as well as the CLS token will have to go through the two attention layers, and these number of attention layers we also verified through ablation study, as well as the number of attention heads to basically configure the transformer architecture as well. So what is the most efficient, most best performing architecture for the encoded transformer encoder. And then, as mentioned, the CLS token represents the video embedding which goes through the classifier. We have used two well-known data sets for this task of video classification. I have to make a comment here that, for example, for ActivityNet, there are videos that have multiple predictions, so multiple labels. But for the sake of this study, we actually looked at a single label classification. So each video was split into shorter snippets, and each snippet or each section will only represent one action. And that's why it was resulted into about 15,000 snippets for the training and validation with 20/80 split, and about 7,600 for testing. And Kinetics 400, it is also relatively well-known, very well used for task of action classification, action recognition or video classification, with videos of roughly the same length, which make it also easier to sample from them the same number. For the implementation, we have used PyTorch for the training pipeline, and pre-trained models are originally trained on and are offered in TensorFlow, but there are versions of them also available, I believe, in PyTorch as well. And for all the experiments, we used a single GPU with this configuration, and also a quad-core CPU for further processing and pre-processing of the samples of the frames. For the ablation study, as I mentioned, a transformer architecture configuration as well as backbone choice as done using the first first data set, ActivityNet, and runtime analysis using Kinetics, because it has videos of similar length and it would make it more realistic, basically. Now to look at some of the results. BTC was the name of the training pipeline that we have in this project. As you can see, without basically fine-tuning the backbone and just using it as they are, even though it offers relatively close results to the state of the art, but it is still obviously behind, which means that these are all the models that are fully trained on the target data set, in this case, ActivityNet. And that's why a lot of researchers have also looked into fine-tuning the backbone slightly, or maybe combining some features to see if any improvement can come out of it. All of these methods have a ResNet type backbone, and they only reported their GFLOP results for the training part, not the feature extraction part. And as you can see, that at least the training part is way more affordable in comparison to the other ones. However, when including the actual feature extraction part, because it is also such a large model, in this case, a ResNet 152 was used, SimCLR, with 50 frame samples for dataset Kinetics 400, it actually increases the computational costs quite a lot. But in comparison to a similar approach, which was done on the same dataset, we can see that it is still more affordable in terms of GFLOPs, but it is not coming close to the the performance level of these models. These two last ones, they are fine-tuned they have fine-tuned feature extractors. The second approach has a fixed feature extractor, but it was trained on ImageNet 21,000, not ImageNet 1,000. And it was also a transformer-based model. So that is the reason why it's actually outperforming this SimCLR model. Um, just very quickly going through the ablation study, we did some on the sequence length, like 16 frames per video, 32 and 128, as well as how many layers of attention had, and what would be the optimal dimensionality of our embeddings that come out of each frame, as well as not having any dimensionality reduction or having just a linear dimensionality reduction, and comparing two of different kinds of SimCLR models with ResNet 50 and ResNet 152. And the best configuration was basically 128 with 2 layers of attentions, 1 attention head, with a learnable layer of dimensionality reduction from 4096 to 2048 and ResNet 152. And for the time analysis, as you can see, SimCLR has quite a lot of a number of parameters and makes the GFlops go to the roof. But the training part is actually very, very lightweight, which means that it can be paired with other feature extractors or other pre-trained models and then already give relatively decent inference or good results, good performance. About 77 minutes to train one epoch, about 35 epochs to converge on kinetics 400, and validation about 5 minutes. And for inference, even though using this large model, it would take about 3 seconds per video to perform inference on a 1 minute video on average. Just to conclude and just mention what we can do to extend this work. As mentioned, this was to assess the generalization of these pre-trained models, which are trained on image data set in a self-supervised way, which means they haven't had any specific task or specific labeled data. They just used unlabeled data. Um, but obviously just checking one type of feature extractor is not enough. Therefore, we plan to include more self-supervised feature extractors, such as this model bootstrapped to your own latent, which has a slightly different idea behind it, where they just abandon the idea of having negative samples in the contrastive representation learning and just focus on the positive samples and finding right augmentations. As well as that, as I said, the training part is quite affordable, which means that we can combine different features, different representations, and then repeat them especially for the task of action recognition. It is obvious that there will be a person performing the action and usually an object. So including models that learn representations about a human, like pose estimation or like object detection together could potentially improve the result. What we have seen is that fine-tuning will definitely improve the results to the target data set, and employing some strategy to sample properly from the frames so that we can reduce even the feature extraction GFlops even more by having extracted important frames instead of taking 128 or 50 or whatever number that was used, and therefore make it even more efficient. Thank you very much for your attention, and yeah, I look forward to your questions.